Hello, so I think we'll begin. I think we've wasted enough time. Yeah, so hopefully we'll do um, another exercise, and then on Thursday we'll finish up with some notes, and then we'll see how we go from there. But yeah, so we're going to finish up from where we ended, and then yeah, we'll move from there. So we talked last time we met, we discussed, we had an exercise, and then we're trying to find expressions of E, we're trying to find V, which is what we're going to do today. As also that you just, excuse me, you just have an idea of how we get to answer and how, yeah, we tackle such questions. So we're going to finish up with the third exercise for calculating SHA. So it was the same question as this, just answered differently. So we're still trying to find SHA, but this time why you're not using the other method. The other method was a bit long and it had a lot of things or issues coming up. But this one, when we introduced theorem Descartes helps us find get to the answer easier. So that's one of the advantages of knowing how to use theorem Descartes. So the last time when we were doing theorem Descartes, I mentioned that theorem Descartes can only be used on closed surfaces. So in our question, we had a line, we had a wire actually, and then we're trying to calculate the SHA at a certain point P, r distance away from the wire. Let me just go to the drawing. Yeah, so we're trying to calculate E and V are distance away from the R, which is this from here. This is the wire, and this was the distance to the point charge, which is P, which is what we're still trying to do, but we're just using theorem Descartes, and we'll see how we go about it. So yeah, so that was the first method. So sometimes they can tell you use both methods, or they just tell you they specify saying use theorem Descartes, or use the reasoning by symmetry, which is what we did the last time, where we used symmetry and then we had to make some conclusions and come to the conclusion. So yeah, we'll use theorem Descartes today, which is what we're going to do. So yeah, so we go to the question. Just calculating SHA E using theorem Descartes. So we have our wire still. We have our wire, and then what happens is that when using theorem Descartes, when you want to use theorem Descartes, it can only be used on closed surfaces. So we introduce the cylinder. We introduce a cylinder. So the wire is passing through the cylinder. So the wire is passing through the cylinder of height h and radius r. So from the wire to the any part of the cylinder, the distance is r on the surface of the cylinder. So the wire is passing through the cylinder to the surface of the cylinder. So the distance from the wire, any part of the wire, to the surface of the cylinder is equals to r. So we discussed that the SHA on the SHAM is going to be always, so at the point P on the surface of the cylinder, that's where our point charge is. So we know that at the point charge P, the SHAM is going to be outwards, radially outwards from the point charge, positive point charge. So we're going to have E in this direction. So we're going to have E in this direction, outwards. And then I mentioned earlier also saying that vector ds, the vector of surface area, is perpendicular to the surface of the area. So we have our surface of the cylinder, our ds is always also perpendicular to the surface. So we've got E and ds in the same direction. And then if you have a cylinder, you know that you have the sides and you have the bases. So on the bases, we have ds. Ds is perpendicular to the surface of the cylinder. So we have ds in this direction, the upward direction. But our E, if we get a point charge here, P maybe yes here. So our E direction at this point charge is going to be outwards, also in that same direction. But our ds is going to be in that vertical direction. So we'll see that the ds and the E, they meet at a 90 degrees angle. And then we're using theorem de Gauss actually. So this is our theorem de Gauss. We got flux is equals to E ds, vector ds, is equals to Q interior over epsilon 0. And then we integrate the ds. So we're going to have ES is equals to Q int over epsilon 0. And then for our flux, so for the cylinder, we have the sides and we have the bases. So on the bases, the E and the S, the E and the DS meet each other at the 90 degrees angle. So if we multiply that, we're going to have 0. So if the two vectors are meeting at a 90 degrees angle, our final product of those two is going to be equals to 0, which is what we have here. And then we've got, we have to find it also in the sides, because in the sides they're moving in the same direction, the parallel direction. So we're going to have E ds S lateral, so that's in the sides, and S bars, that's on the bases. So on the bases, we've got E meeting ds at the 90 degrees angle, and the product is equals to 0. And on the surface of that cylinder, we've got E and ds moving in the parallel direction, in the same directions, which is what we have indicated here. So I have flux is equals to E ds, E integral of ds lateral plus E integral of ds bars. So at the bars, we got E meeting ds at the point of 90 degrees. And on the sides, we have them moving in the same direction. And then what we're going to have here, because this is going to give us 0 because they're meeting to each other at 90 degrees, we're going to have flux is equals to E integral of ds lateral is equals to ES. And then our S, the same thing, we do the same thing. Our S is equals to the surface area. So our volume is equals to pi r squared. So our surface area is going to be the derivation of that. So we're going to have 2 pi r h, but this is the cylinder, it has height. So we're going to have 2 pi r h, that's the surface area of the cylinder. So we're going to have our surface area is equals to 2 pi r h. And then if we replace where our S is, we're going to have E 2 pi r h. So we've got our formula ES is equals to Q int over epsilon 0. So I've got epsilon 0, Q over epsilon 0 is equals to ES. So we have what E 2 pi r h. And then looking at our drawing that we have here. So we say the wire is flowing along DL or DZ. So it can either be DL or DZ. And then what we have here is dq is equals to this Greek constant dz. This is lineaic, if you remember. This is lineaic, the constant lineaic surface. Lineaic, yeah, lineaic. So we're going to have, if we want to have Q along the line, because we're now trying to find it along the line, along this line, we're trying to find the charge at this point P on the surface of the cylinder, but from this wire. So we're going to have dq is equals to the constant dz or dl. And then for us to have Q, which is the charge for the whole wire, the charge for the whole wire. Right now we've got dq because we're finding that at a segment, maybe this segment here, but now we're trying to find the integral of dq, which is Q for the whole wire. So we're going to have, because here we have Q, so we're going to have dq is equals to the constant dz, and then for us to have Q, we're going to have to integrate dq. And then we integrate dq, we're going to have Q is equals to, when we integrate this, we're going to have the constant coming the other direction, integral of dz. So as I've mentioned, the Z is the same as DL, which is the height, which is the length of the wire. So if we have the length of the wire, which we've given which is the height of the cylinder, because the cylinder can be from whichever point you have, from whatever point you have. So we have the H, which is the integral of the Z, and that's which is what we're going to have here. So our Q is going to be equals to the constant times height. So where there's Q, you replace with your constant times height, and then when you make E a surgical formula, this is what you're going to have, which is the same as what we had, the same answer that we found here. So just two different methods of getting to the answer. So they might tell you to use both methods, or they might tell you to use one. So yeah, the theorem de Gauss is simpler and it's quicker, but you're supposed to know both of them just for it to be on the safe side. So yeah, are there any questions?
There's a question.
Sure.
Just scroll up on the diagram.
Oui.
Yeah, like what makes the non-can, the direction of the DS to
Of
be
the what?
different
DS.
between the bases and the ratios? Like what makes them to be different?
Because we have, I said, okay, I get your question. So I said you must always know that any surface, it might be a round surface, it might be the surface, on any surface, the direction, if you want to draw the direction of the surface area vector, it's always perpendicular to the surface to that surface that you're trying to calculate. So we have, this is our area for this bars, but our direction, our vector, when we want to draw the vector for the surface area, is going to be perpendicular to that surface. So here on the bars, this is a cylinder. A cylinder, it has the bases and the sides. So on the base, the DS is perpendicular to the bars. So we're going to have the DS vector moving in the vertical direction. But then if we have a base, our E, maybe let's assume our point P is here. We pick our point P here. Our E is going to be still outwards, in the outward direction. So our E is going to be in the outward direction, but our DS at the base is going to be perpendicular to the point. So it's going to be perpendicular to the surface. But on the sides, if we're trying to calculate our point P here, this is our point charge P here, on the surface of the cylinder, our E is going to be outwards and our DS is going to be perpendicular to the surface, which is what we have here. So E and DE that moving in the same direction in the lateral side. So in the lateral side must be of a sphere or of anything. The E and the DS are always moving in the same direction, parallel to each other. But on the bases for things like cylinder, a cone, yes, the DS and the E, they cancel each other because they meet at 90 degrees and the product is equals to 0. Is that okay?
Okay, it's okay.
Wait, so are there any other questions?
Yes, kindly explain on the DS again, because there's a point where you found 0. Then explain on it. How did you find 0 and which DS are we putting into consideration on the diagram?
Okay, so theorem de Gauss is equals to so theorem de Gauss is equals to this E. Okay, theorem de Gauss is equals to E. Okay, we have it here. Let me not even try to waste time. So theorem de Gauss is equals to this. So E integral of ds is equals to Q int over epsilon 0. This is our theorem de Gauss. But then we have a wire. They're telling us to find the E and the V at a point P that is our distance away from the wire. So they're trying to make us find the E that is being produced by this point charge and the potential that is being produced by this point charge, which is R distance away from this wire. So we have the wire. So using theorem de Gauss, I said again saying theorem de Gauss can only be used in closed surfaces. So if you have a sphere and if you have a cylinder, you can use theorem de Gauss. So here we have our cylinder. We introduced our cylinder, and then our wire is passing through the middle of the cylinder. So which is what we have here. And then we've got a point P on any surface around this cylinder. So we've got a point P here, or we can, on the bars, we can say it's here. So we'll start with here. So if it's on the bars of the cylinder, we're going to have E moving in the outwards direction. And then our ds, our vector ds, our vector surface seek is always perpendicular to the surface where it's been written from. So this is our surface. Our ds is always perpendicular from the surface. So the surface and the vector ds, they meet each other at 90. And the E vector is always outwards, as I mentioned, for a point charge, the E is always outwards. So we're going to have E and DE flowing in the same direction in our sides, in the sides. So if we have a cylinder, we have the bases and we have the sides. So on the sides, we established that the E and the DS are moving in the same direction. But on the bars, it's different because we have our area here and our DS is going to be moving perpendicular to that surface area. So they're going to be meeting at 90, but our E is going to be moving in the same direction. So if we get a point, we assume the point P is here, the point charge is here, our E is going to be moving in the same direction, but our DS is going to be moving upwards, I mean in the vertical direction. So the E and the DS will be meeting at a 90 degrees angle. The vector Champ and DS, which is our surface area, will be meeting at a 90 degrees angle. So if we have our theorem de Gauss, we have vector E integral of ds is equals to Q int over epsilon 0, which is what we have here. So if we integrate ds, we're going to have surface area. This is just ds is petty surface area. So we're going to have E integral of ds is equals to, if we integrate ds, we're going to have S is equals to Q int over epsilon 0. But for our cylinder, we have the bases and we have the sides. So we're not going to ignore that fact. So we put that fact into consideration. We have our flux is equals to EDS lateral. So this is the sides, the lateral is the sides, representing the side, the surface area S of the sides plus the S of the bases. So we're going to have, we've established that the vector E and DS and the lateral is parallel, which is what I've indicated here. So E and DS are in parallel, plus the vector E and DS on the bases is perpendicular to each other, and the multiplication of perpendicular vectors is going to give you 0. So we have E and DS. E is perpendicular to DS, which is going to give me 0. So I know that EDS on the side is going to give me this, and EDS on the base is going to give me 0. So I'm just going to have EDS in the sides, which is what I have here, I've indicated here. I'm going to have E ds S lateral is equals to ES, which is the same as what I wrote here. But you have to show this because you have to show them that you're dealing with a cylinder. So you have to know that they have to know that you're dealing with a cylinder. We have the bases and we have the sides. So we have E ds S lateral is equals to ES because the base is equals to 0. The multiplication of this vector and this vector, the integral of this vector is going to give you 0. So we have ES is equals to Q int over epsilon 0, which is our theorem de Gauss. So if we have this, our S, our surface area, expression for surface area of a cylinder is 2 pi. The volume is pi r. The volume is pi r squared. I think we did this in normal math. So the volume of a cylinder is pi r squared h. But if you want to find the surface area, you differentiate this. So you're going to have equals to 2 pi RH, which is our surface area of the cylinder that we're going to have. So when I have this, I'm going to, where there's my S, I put my 2 pi r h, which is what I have here. And then I'm going to go back to my formula. I have Q int over Q, which is the charge internal, over the epsilon 0 is going to be equals to E, but my S, already found my value for S. So I place where there's my S, I put what I found. And then for my Q, I mentioned saying this is the cylinder. So we have dq, this is linear. So we're trying to find it along this line. So now we have linear, we're using linear. So we're going to have dq is equals to the constant dz, but then we have q here. So we do not have, here we have dq. So for us to have q, which is the charge along the whole line, we're going to have to integrate our dq for us to have q. So we integrate both sides. We're going to have q is equals to, this is a constant, so our integrating with respect to dz. And I mentioned in that in the first exercise saying dz can be, the line can either be dz or can either be z or l. And then when you get a section or a segment of it, you have dz or dl. So in this part, we'll say this is dz, which is our length of the wire, which is what we have here. So if we integrate dz, we know that we're going to have the whole wire. We're going to have the whole length of the wire, which is the same as the height, which is what I indicated here, the height from wherever to wherever. So that is what we have there. So we've integrated dz, we have the height. So our q is going to be the constant times the integral of dz, which is our height, which is what I've replaced here. So I have E 2 pi RH is equals to Q, which I was replaced by the constant and H over epsilon 0. And I just changed the sublevel formula for me to have E. So the H, this H and this H will cancel. And then I have constant is equals to over 2 pi R epsilon 0, which is equals to our SHA, which is the same as the one that we found in the previous exercise. This guy here. So are there any questions?
Okay.
And there's another question.
Sure.
Kindly repeat once again on the where I've said that the DS and the E, where they're perpendicular, the non-tan is equal to 0.
On the diagram.
Yeah, I have said that if they're perpendicular, the shan is equal to 0.
Yes, so
Kindly explain once again.
If I have a surface, sorry. If I have a surface, any surface, so it might be just a normal surface. I have a, sorry. Oh my God, okay. I'll try to draw it again. So if I have a surface, any surface, this is my surface. So if this is my surface, I'm going to know that for me to draw this is ds. Let's say this is ds. This is a small surface ds. This is a small surface ds. So I know that for me to have the vector representing ds, the vector representing this small surface area that I have here, the vector is always going to be perpendicular to the surface. So if I have a surface like this, the vector for ds is going to be perpendicular to the surface, which is going to be this direction. It's perpendicular to the surface of ds that we have here. This is our surface. So our ds vector, the vector ds, the vector representing the surface area is perpendicular to the surface. So if I have a surface for this, in this example, we have a cylinder. So a cylinder has two sides. We have two surfaces. We have the bases, two bases, and we have the sides. So in the sides, we have the ds, which is perpendicular to the surface. This was my small indication. So we have ds, which is perpendicular to this surface in the sides, which is moving in this direction, and our E at this point is also moving in the same direction as ds. But then we have the bases. On the bases, our ds is going to be moving upwards because it's going to be perpendicular to the surface. And then our E at this point, we assume there's a point charge here, P, on the base of our cylinder. The E is going to be moving in the outward direction from the point charge, but our ds, our vector ds surrounding that charge is going to be perpendicular to the surface area. So it's going to be perpendicular to the surface where the charge is, which is what we have here. So this E and D and DE are meeting each other at 90 degrees. They're perpendicular to each other. And the multiplication of the two vectors, because they're perpendicular to each other, is going to be equals to 0. But in the sides, we have two flowing in the same direction. So we're just going to continue with our calculation because there's no cancellation going here. They're not going to give us equals to 0. They're moving in the same direction, which is what was being talked about here. Which was what is being talked about here. So you could have just gone straight, but you have to indicate, since you introduced the cylinder and you want to use the Gauss theorem, which is a bit simpler and doesn't take much of your time. So you indicate that you're using a cylinder. So they have to know that you know what you're doing. So you have to show that for a cylinder, we have two sides. We have the sides and we have the bases. And the bases, the multiplication of the SHA times the ds, which is our vector for surface area, is going to give us 0. So it's just the same as having E ds, E integral of ds is equals to Q over E, because this and this is going to be equals to 0. But you have to indicate this, which is going to be equals to our flux is equals to E ds, which is the same as S, because when you integrate ds, you're going to have S. So when you find your S, you find your volume for your cylinder, and then you integrate, or if you know it, you have to know it. So our surface area for a cylinder is 2 pi RH, which is gotten from the integration of the differentiation of the volume. So we have 2 pi RH where there's our S, and we continue with the whole process. Have I answered your question, or you have another question?
Okay, it's answered.
Shawans,
Sure.
sorry to take you back. Can you kindly show me the previous answer we found for E?
Okay. Thanks there.
Oh.
That's okay.
Yeah, it's okay.
All right, so you can use two methods. If they want you to use both methods, they'll indicate use theorem de Gauss or use asymmetry, which is the first one that we did, where we indicated that asymmetry, because we indicated that. Kindly mute your mic.
Also.
Okay. Well, we indicated that we have the vector of E moving in two directions. We've got it moving in the E direction and in the X direction. Sorry. Yeah, we have it moving. Let me just try to go. Yeah, so we have it moving in the X direction. We have it moving in the Z direction, and we know that the Z and Z cancel. So we're going to have it just moving in the X direction. So yeah, the Parizon symmetry. So they'll tell you use Parizon symmetry or use theorem de Gauss to solve whatever question you've been given concerning SHA, and that is how you go about it. So yeah, so we'll go to today's, and then probably on Thursday we'll continue or we'll conclude. Yeah, so we go to today. So today is we're trying to find, we have a disk uniformly charged with radius A that carries the density superficial décharge, which is that constant. And they're telling us to calculate E and calculate V. So these questions are common. We usually try to calculate the electric charge, they try to calculate the potential or the charge. Yes, so we have E and we have V. So they're telling you to calculate the E at a point P situated on the axis of the disk. So we have a disk and we have this axis, yes, in this direction. So we have a point P on the axis of this disk. So we have the disk, we have the radius, and we have the length from, sorry, this is a bad drawing, have the length from the center to P, which is denoted by Z in this case. And then they're asking us to also deduce V. So yeah, so what we've been given is that we've been given the density superficial décharge, a constant, and then we've been given the radius only. So we'll work with that. So we have, yeah, so we go with that. So we have for Z is greater than 0. So here we know that Z is in the positive, so Z is greater than 0. So we have a point charge Q. This is just some explanation. So we have Z moving in the OZ direction because they've given it the distance from the point, from the center to the point PZ. So we just say this is the OZ direction. So this is the Z direction. So we have if Z is greater than 0, we have Q, and then this is our point charge, and then we have we're calculating it at the point M. We're trying to calculate the E and the V that is being produced at this point, that is being produced by this point charge. So which is what we're going to have here. So remember our E, our formula for E, our electric charge is equals to 1 over 4 pi epsilon 0 Q over R squared in the direction U. And then if we're having dE, so meaning we're going to have dQ, so we're going to have 1 over 4 pi epsilon 0 dQ over R squared in the direction U. And then they've given us density superficial, which is our surface area density. So we're going to have the constant is equals to dQ over ds. So we know that if we make dQ a sublayer formula, we're going to have the constant times ds, which is what we've replaced here. Where there's dq, we've just replaced with our constant ds in the direction u. Yes, so u, we go back to our mechanic to power our repair. So we have u. How is u moving? So in my drawing here, just a moment. In my drawing here, as you can see, this is z is greater than 0. So we have z is greater than 0, so meaning z is positive. Sorry, let me just indicate my z. So my z is positive. And then I'm finding the let me just a minute. Back to the question. So we're going to find the E on the axis of this disk. So what we're going to do first is that we're going to introduce R. We're going to introduce both our R's. So we have R, a distance in the disk and out of the disk. So it's like the same thing. We're trying to find the sump in the interior along in the disk and out of the radius of the disk, which is along the point P. So what we're going to do is that we introduce our another point. So we have our R inside the disk, which is what we have here. So we introduce our R, which is less than our A, and then we introduce the vector of our sham to our point P actually. So now we're trying to calculate the sham. So what we're going to have here is that with our U, we're going to introduce our vector U, which is moving in the sham direction. So we're going to have U, the vector U is moving in the sham direction. So we have U moving in this direction. So what we're going to have here, for us to have our U, we introduce our trig. So we're going to have a vector here, or an angle here, which is our Q, which is our theta, I mean. We're going to have our theta here. We introduce an angle there for us to have U. So we have our U moving in this direction. So we have our U moving in this direction. Yeah, so we have our U moving in this direction. So for us to have our cos K and our negative sine J, what did we do? So we have OZ moving, we have this from the center to our Z. I've given this direction to be Z, so I take this ax to be ax OZ, which is indicated, has been indicated by that Z. And then we know that there's also the ax moving in this direction, in the vertical direction. So we're going to have, for us to have our trig, we're going to introduce this line here. So we're going to have an angle, we're going to have our trig here, and then we're going to come up with our cos theta K minus sine theta J. So we know that for us to have U, which is our U in this direction, we're going to have to add the adjacent plus the opposite. And then when we added our adjacent is equals to cos theta Z. And you remember in our Cartesian, if we have Z, our base repair can be EZ or can be K. So in this situation, we had Z. So our cos theta was going to be replaced by the base, the unit vector K, which is what we have here because it's moving on the X, in the X direction on the X axis. And then if we have a vector, yes, we have it moving in this direction, we're going to have either X or Y. So in this case, we used Y. So we have our opposite is equals to negative sine J because it's in the negative part of what we're trying to calculate. So we're going to have negative sine J because it's in the negative part of our what we have here. So we're going to have this and we're going to have this. So which is what we have here. So we have U is equals to cos theta K minus sine theta J. That's where our that is coming from. So we're going to continue with our equation. So we're going to have dE, where there's U, you put your cos K and your sine theta J, which is what I have here. So I have dE is equals to cos theta K minus sine theta J. Then par raison de symmetry, what we did. So we know that if I have E here, so I can have a point here. So the E is moving, the E here can be moving in the X direction, in the Z direction, in this case, in this Z direction, and can be also moving in the Y direction. The same here, if I extend the point from here, from this, let me draw it, from the negative direction, if I have a segment here, I can extend it and then I'll have E moving in this direction also in the X axis and also in the Y axis. So that's why we're using reason symmetry, which I explained in the last exercise. So from that, sure.
I'm a bit lost how it came up with U to be the one that's like diagonal.
U to be the one that's what?
That's like diagonal on that triangle that you made.
So we have our SHA. So our SHA is the vector carrying the U. So we're going to, our SHA is the one we're going to give the vector, the base vector U. Do you get what I'm saying? So here we have our dE. At this point from this disk is moving in this direction. So we draw the vector from the disk to the ax of the point that we're trying to find, so the point charge is. So the dE is going to move in outwards. So if we have the dE moving outwards, our vector U is also going to be in this same direction. It's going to be our dE, our base vector of dE is going to be U. That's how come we have U.
So what's that point P code?
It's the point charge. That's where we're trying to calculate our our E, the E that
Oh,
being
so our P is
charge
going to
P.
come from that point,
Yeah.
following the direction of E.
Yes.
Okay.
Yes. So that is what we have. And then what was yes, so Parizon the symmetry E serapote palax OZ. So we know that this in this direction and as I explained in the last exercise, so I'm going to have in this and this direction are going to cancel. So I'm just going to have E being carried by EZ. So which we're going to have here. So we're going to have dEz is equals to 1 over 4 pi epsilon 0, the constant ds over r squared cos theta k. This is going to be equals to 0. So after this, we're going to have dEz is equal to 1 over 4 constant ds r squared cos theta, which is what I have here.
Wait, I have a question.
Sure.
Where are you getting this 6D?
It's not, it's a constant, it's not 6. It's the constant for, we have, when we're trying to calculate charge, we have charge volumic density, we have charge surfacic, and we have charge lineaic. So for charge volumic, we have the rho constant. We have our rho is equals to ds over dv, and we have that constant. That's for charge volumic, and then for charge surfacic, along we're trying to calculate the charge, that's charge from a certain surface area. We have this constant, and then for lineaic, we have the other constant that we're from dealing with in that other question. We have this constant for lineaic along a line. So we have this constant for lineaic, and we have rho for volumic, and we have this constant that usually when I'm writing fast, it ends up looking like a 6, but something like this constant, the Greek constant, looking like this, which is equals to the charge, like that's the charge along, or yes, along a certain surface area, which is what I have here.
Okay. Does it mean that it's the same one which you wrote inside that circle
Which
with the
circle?
direction? Where there is a radius, then on the other side. This circle
No,
where,
this one.
yes.
No, it's not there. This is my point P. Well, I'll continue explaining. This is my radius A. This is my direction. This is my K direction. I mean, sorry, I wrote it here. This is my K direction. This is my OZ. So I have my K direction, and this is my DE, and this is my theta. So I'll explain all that as we continue. But yeah.
Wait.
Yes. So
What is this sim?
which one? This one.
Yes.
That's K. That's the vector. This is the K that we have here. This is K, and this is R.
Okay.
This is
And then what is the Z representing?
the Z is the distance from the origin of the disk to the point charge Z. So from the origin of the disk to the point charge Z, to the point charge P, we've moved Z. Yeah, we moved, it's like R, but from this time we gave it Z. So we also assume that the axis on which it's moving, we're also going to have it in the OZ direction, which is what we have there.
Sorry, but I didn't get the explanation as to when he asked why isn't 6 I didn't get, as in the network was cutting, so I didn't really get the explanation there.
Okay, so it's not 6, it's a constant. I don't know how. So it's something like this constant. It's also something like this constant. It's not 6, it's a constant. So we have remember when I told you when we have charge, it's either we're having charge from a certain volume or from a certain surface area, or the charge is along the line. And then we have the three constants. We have rho, we have this guy, and we have lineaic that we adjust from doing. So we have lineaic, which is something like this, which we're just from doing. That's along the line. We're trying to calculate that's the charge along the line. And then we have rho from a certain volume space, and we have this chart, this one that looks like a 6 usually when you're writing it fast. So we have something like this, which is what I am writing here. So from here, present the symmetry we explained in the first exercise. So that is what we've used here. So we're going to have E is equals to EZ, and then we're just going to have cos, because this guy is canceling out, is going to give us 0. So we're going to have dEZ, sorry, we're going to have dEZ is equals to 1 over 4 pi epsilon 0, the constant ds r squared cos theta, which is what we have here. And then we're going to continue. We have, sorry. Just a minute. Okay, so yeah, so our dEz is going to be 1 over 4 pi epsilon 0, the constant r squared in direction cos theta. So now this is where it gets tricky. So we have in our direction Ez, so we have this 0 is less than r is less than a, is what I've indicated here. Is what I've indicated here. So we have our a, so we have 0 is less than, we have 0 is less than r is less than a. So when we're trying to find E or V, usually we have to find it in reference to another point, which is usually why we have two spaces here that we're using. So when we're trying to find the E being produced by this point charge, we have to, usually we make it in, we find it in relation to another point on that day. So here we have this point that we used on the disk for us to be able to calculate our point charge, our E being produced by this point charge. So we're using in reference to this point here, the point charge being produced, the sham being produced by this point charge, and the V being produced by this point charge. So we have 0 is less than r, which is less than a. Our a is our radius. So we have our r, our distance from the point charge to any other part of the disk which is not giving us the full radius, because we know that the radius is from the origin to the surface of the disk that you have. So this R is less than, we've gotten an R less than the A, so which is our indication here. So we have our R is in between A and 0. It's not our radius, so it's not qualified to be called our radius because it's in between our 0 and our radius, which is the referential point that we've chosen for us to calculate our E being produced by this point charge. So which was this drawing. I'm sure you've seen this drawing. So if we're trying to calculate the sham being produced by this point charge at by the charm being produced by this point charge, we're going to use another point charge in referential to the point charge. So which is what we're doing here. So we have 0 is less than R, which is less than A. So yeah, that was our first indication. So we have our dEz is equals to 1 over 4 pi epsilon 0. Our constant R squared is cos theta. So we have ours for our 0 is less than R is less than A. We have dEz is equals to, we introduce our limits, because for us to, now we have to find our E. We're not trying to find our dEz. So we have to integrate our dEz for us to find our E. So if I integrate my dEz, I integrate this side, I'm going to have E. If I integrate this side, I'm going to have this, what I have here. So we have our E is equals to Ez, which is equals to our constant over 2 epsilon 0. So we bring our constants out. We're going to have what we have here. So for us to have what we have here, so we have 1 over 4 pi epsilon 0, our constant ds cos theta over R squared. So for our ds, we're going to have our surface area for a disk or a sphere, which is what we have here. So our surface, if we have our volume for a sphere, our volume for a sphere is equals to, sorry. So this is a disk. Yes, so we have a disk. So our surface area, sorry, that was cut. So our surface area is going to be pi R squared. It has no height, it's just a mere disk. So we have our surface area is going to be pi R squared, and our ds is going to be 2 pi R in the direction dr with the dr. So it's going to be our s, let me write it down. So our s is equals to, our s is equals to pi, so our s is equals to pi R squared so for us to find ds in the direction of, this is pi is a constant, so we have R, so we're going to have ds. So we're going to have ds, oh my God. So we're going to have ds, ds over dr is equals to, we're just differentiating ds is equals to 2 pi R. And for me to have ds, I'm going to have ds is equals to 2 pi R dr. So I've just multiplied this dr this side, which is the same thing that I've done here. So I have ds, my s is equals to pi R squared, and my ds is going to be 2 pi R dr, which is the same thing that I'm showing you here. So where there is my ds, I'm going to add my what I have. So I'm going to have my constant ds is 2 pi R dr times cos theta, which is what I have here. So I'm going to have from 0, which is less than r, which is less than a, I'm going to have my constant over 2 epsilon 0, which are my constants, integral from a to 0. So from a to 0, my limit is from 0 to a, r dr over r squared cos theta, which is what I'm going to have here. And then now I'm trying to find the value, I'm trying to change r and dr in function of theta. So I'm trying to find r, small r, and big R in function of theta. Small r, which is my radius. So I'm going to have tan theta is equals to r over z from our diagram. So my diagram, I have my diagram. Here I have what I have here. Sorry, I'm going to have. Okay. So on my diagram, I have this. So for me to have tan theta, I'm going to have tan theta is equals to opposite over adjacent. So my opposite for this theta, this is my theta here. So tan theta is going to be opposite, which is my r, my grand r over z. Z is from 0 to p. So I have r over z, which I have here. So which is what I have here. So I'm going to have this. So I'm going to have tan theta is equals to r, the grand r over z. And then when I make r, because I'm trying to change r and the r in the function of theta, I'm going to have r is equals to z tan theta, which is what I have here. So for me to have dr, I have to integrate, I have to differentiate r. And if I differentiate tan, I have my differentiation of tan, if you remember trigonometry, differentiation of tan is 1 over cos squared theta. So differentiation of tan is 1 over cos squared theta. So for me to have dr here, I have to integrate with respect to theta. So I'm going to have z over 1 times cos squared theta d theta, which is my dr. And then where there's my dr, I add my dr. So for my dr, I replace with my value here, which I'll put in my dr. And then for cos, my cos is equals to z over r. So I have, let me go back to my, sorry. So my r was from my equation. So I'm going to have, so I have that. So I'm going to have, sorry, I forgot to mention my r. So I'm going to have my r. Yes, so my cos theta is going to be the cos theta is equals to adjacent over hypotenuse, of which I'm going to have as my adjacent, which is my z over my r, which is what I have here. Yeah, so which is what I have over here. Which is what I have over here. So I'm going to have cos theta is equals to z over r. So my r squared, this r squared, which I'm trying to change, is equals to z squared over cos squared theta, if I make r the subject of the formula. So which is what I'm going to have. So if I replace where there's my dr here, I put this value, and then where there's my r squared, I put this value. We'll see what I'm going to have. So I'm going to have, this is what I'm going to have. This is what I'm going to have. So where there is my, where there was my r, I put z tan theta, because that is what we found as our value for r. And when there's our dr, I put z over cos squared theta, which is z over cos squared theta d theta as my dr. And where there's r squared, I replace with z squared over cos squared theta, which is what I have here, times cos theta that we already had. So from our constant over 2 pi epsilon 0. So they've just changed the limits. It was from 0 to r. So now you can just say from 0 to r, we have 0 to theta to theta. Our theta I is this angle here. Because you know that your I is your radius. So meaning we have from 0 to r is our theta. So 0 to our a, which is our radius, because you know from the center to any part of your disk is supposed to be a radius. So we have from the radius to the point P through the point E, we're going to have Q1, which is our angle here. So we're going to have the same thing, which is what we have here. So yeah, we have that, which we have here. So when we simplify this, we're going to remain with sine theta d theta, and then we're going to have our constant integration of sine theta is equals to negative cos theta. So we have our limits. So if we replace with our limits, you know, you have to subtract. So when you replace with 0, you're going to have 1, and then when you replace with theta, you're going to have theta 1, you're going to have theta 1. So we're going to have E is equals to our constant over 2 epsilon 0 times 1 minus cos theta 1. And then we already talked about the value for cos theta. So our cos theta at first was gotten from here. So now we've got, we're trying to find our cos theta 1. So our cos theta 1 is, we're going to do the same. So cos theta 1 is this angle here, this bigger angle. So cos theta 1 is still the same. It's going to be, cos theta is adjacent, so it's going to be our rho. So our distance from A to through our point P is rho. So we're going to have rho over Z. So which is our value for cos theta 1, which is what we have here. And then we're going to have cos theta 1 is going to be actually Z over rho. And then our rho, we know that our rho is equals to Z squared plus S squared. And if we have to have our rho only, I'm going to have square root. So for me to have rho only here, I'm going to square root both sides, which I have here. And then my cos theta 1 is going to be Z over Z squared plus S squared. And my E is finally going to be equals to my constant, here over 2 epsilon 0 multiplied by 1 minus my cos theta 1 is equals to Z over Z squared plus S squared, which is what I have here as my shan. So are there any questions, any queries, or any additions?
Sorry.
You mean whatever which is in the inside there in the brackets was just equal to sine theta d theta.
Sine theta, yeah. This, when you simplify it, this is going to cancel the Z, this Z and this Z is going to multiply. So the Z's are going to cancel. So we're going to have tan theta d theta times cos theta. And then when we, tan theta is equals to sine theta over cos theta. So the cos and the cos is going to cancel. So we're going to remain with sine. So this, the Z's will cancel, the cos thetas will cancel, the cos squared thetas will cancel. So we're going to have something like this. We're going to have equals to tan theta. We know that tan theta is sine theta over cos theta. Sine theta over cos theta. So we're going to have sine theta over cos theta is times cos theta, because that cos will still be there. So we're going to have times cos theta. And then you know that this and this is going to cancel. So you remain with sine theta d theta, which is what we have here. So we're going to, this Z and Z are going to have Z squared. So the Z squared and the Z on top will cancel. This cos theta and this cos theta will cancel. So we remain with tan theta d theta times cos theta. And then you know that your tan is equivalent to sine theta over cos theta. So you're going to have sine theta cos theta d theta, which is this our d theta here times cos theta. So our cos's, when we write tan, We simplify it and we're going to have our cos, and our cos cancel. We're going to remain with sine theta d theta. And then when you integrate your sine theta in with respect to the theta, we're going to have a negative cos theta. Sorry. Are there any other questions?
Then on how to write tan theta, I think you should be writing it the way we are used to.
No, but you
TAN.
need to write it like this in your faculties.
Oh,
Yeah,
okay.
TJ
Okay
theta.
then. Thanks.
Okay. Which is what I have here. So if there's no more questions.
Sorry, just out of curiosity, how many marks are there for this question? Like approximately, if it was an exam, what speaking about?
Usually they'll just give you like 3 of these questions for an exam, like 3 of such questions for an exam. So an exam is out of 20. So maybe one question will carry 5 marks. So you have to really show with the steps and indicate, because just in the steps they'll get marks. So usually you have maybe 5 marks for one, or if you have a very involving question like the one that we were doing last week, maybe it can have 7, 8 marks. Just one question, because it takes up a lot of time. But maximum you have maybe 4, 5 of such kind of questions. Yeah. So
What do you mean? You mean questions like exercise 1, then that's one question, or just this whole question as one?
just this whole question as exercise, as in like the questions we're doing the last time, we had 2 questions, right? We had 2 questions for finding E and V. The same thing, we're finding E and V. Maybe that's question 1. They bring for a diagram. That's question 1, find the E and V. And then another question, question 2, the same thing. Maybe they tell you to calculate other topics that are in front for capacity, for everything. That's question 2. So you have something like this, also question 2. And then you have question 3 again. So like this is just question 1 of exercise 1. Like you have exercise 1, exercise 2, exercise 3. So exercise 1, question 1 is this. And then just like that. So you don't have a lot of exercises. Maximum is 3 exercises. Or 4. Or 4. But yeah.
Thanks. Sorry for asking many questions. So,
Nice.
from what I've been seeing, I've just been driving there. The answers themselves, they are just expressions. So,
Yes,
there are
just
no questions where you even find the values in numbers.
yeah. Okay, from what I have done at my school, we are never given numbers where we have to deal with numbers. Usually they just want to know if you know how to come up with a certain expression or E or whatever it is that they want you to find. But if they give you values, so meaning you still have to calculate it the same way, and then at your à la fin have to add your values. So you still have to do the same process. Then at your à la fin you add your values. You substitute your values. But usually they just give you expressions and just check to see if you actually really know what you are doing. Okay, so that's for our E. So for our E, that's what we have. So don't forget the direction. So I have E and the direction, the car direction. Yeah, so that is what we have. So now we have if z is less than 0. So if z is less than 0, so meaning the z will be on the negative part. So our z in this guy right here was on the positive side. So we have our z. Our z is this guy here. This guy from O to our point charge. So from O to our point charge is our z. So our z will calculating z greater than 0. So here you show your z less than 0. So for z less than 0, so our z is going to be on the negative side of the disk charge. So if z is negative, we're going to have the same calculation, but the only difference is that we're going to have a negative for if z is negative, if z is less than 0. So we're going to have a negative. So you can follow the same calculation and you can send me the answer afterwards. And then your z is going to be negative. So we're going to have our E, our modulus of E in the direction Ez is going to be this. This is what we found for the z is greater than 0, if you can see here. But if our z is less than 0, we're going to have modulus of z. So modulus of z, you know that it's either positive or negative. So for the fact that we have a negative z, we're going to introduce our modulus. So this also means that our modulus means that the z is negative or positive. So here, so here I don't have this. So we do not have our z. So if that's the case, if our z is negative, so we're going to have a negative multiplying the whole expression without the modulus. So we're going to have negative multiplying the whole expression. So if we have a negative multiplying the whole expression, we're going to have for z is greater than 0, we're going to have this, which is our normal expression that we just found. And for z is less than 0, we're going to have this that we have here. So we're going to have the negative multiplying the whole expression, and we're going to have negative the constant 2 epsilon 0 minus, so the negative multiplying inside here, we're going to have minus this minus z over the squared plus a, which is what we have there. So yeah, so that's going to be our E for the both for z is greater than 0 and z is less than 0. And then our V, these are limits, so our V. So for us to deduce V, have you guys done limits in analyze?
Not yet finished.
Not yet what?
I'm not yet done with it. We're still doing it.
Okay, so you're still doing limits.
Yeah.
Okay. So we have, for us to deduce our potential, we're going to have our expression E is equals to negative grad of V. So this is a very important expression, if you've noticed. So it's usually when they tell you to calculate SHA, the next question will be calculate V. So you have to know the expression that connects your SHA and your V. So we're going to have in the du which is our second equation. So we're going to have our expression that relates, that has both E and V. We're going to have E is equals to negative grad V, which is what we have here. So our E in this equation, our EZ, so we have it in the K direction. So we are following which repair. So we're following the Cartesian repair. So we're going to have EZ, we're going to have it in EX, EY, and EZ. But since our E is in the K direction, we're going to have our EZ is equals to negative. Our expression, this negative grad V, and our grad is equals to negative dV over dZ in the K direction, which is what we're going to have here. So if we divide to eliminate the negative sign, we're going to have our expression of E, which is this. Okay, so Oh, the E, okay. So for the E is just representing a small, what can I say? So for our first expression, for our Z is greater than 0, we had 1. And for our second, Z is less than 0, we had -1 because we multiplied by negative. So what they did, they used limits to just simplify the equation, which I thought would be a bit complicated for you because you haven't done limits. So I tried to jump it, but yeah, we tried to just see what they did. So we have our E for greater than 0, we had 1, and for less than 0, we had -1. So what they did is just they replaced the -1 and the 1 by an expression E, a small expression E. So we have here, this is what we have here. So we have E is 1 if Z is greater than 0, and -1 if Z is less than 0. So our whole expression, they minimize it down to the total champ for the Z is greater than 0 and Z is less than 0 is our constant 2 over epsilon 0 E minus Z over Z over what we have here. This E is for both the Z is less than 0, Z is greater than 0. So this E is -1 if Z is greater than, if Z is less than 0, and it's 1 if Z is greater than 0, what we're just from calculating. So that is the E that we have. So if you have, you can replace your E with 1 or with -1. So that's where our E is coming from. So we're going to have our champ here. We're going to have our V, our potential. So we're going to have our potential where there's our E, we put our expression for potential, and where and then we have dV over dz in the direction k. So the k's cancel, and then we're going to have this, and then we're trying to find potential. So we're going to try to leave this guy along the side. So if we leave this guy along the side, we're going to multiply the dz times this whole expression. So we're going to have dv is equals to negative because of this negative. So we're going to have negative the constant over 2 epsilon 0, our expression times dz, which is I've just changed some things here. And then what I'm going to have is, yes, so for me to have v, I have to integrate. So for me, this is my dv. So for me to have v, I have to integrate, definitely, for me to have v. So I have to integrate both sides, but this is a constant, so I have to integrate both sides. I have to integrate both sides. So I'm going to have v is equals to the integration of this. So my v is going to be equals to the integration of my expression that I have, which is this, our constant comes the other direction. So I'm going to have integration of E, which can be 1 or -1, more Z over Z squared plus A squared, I mean, which is what I have here in the direction dz. Or with respect to dz, sorry, not in the direction dz. So with respect to dz. So I'm going to have, so now what I'm doing is integrating. So I know that for me to have, for example, I have z squared. As you practice more math, you will be able to, yeah. So I have z plus s squared. The integral, the differentiation, the integral, I mean, of z plus s squared is equals to what we, this is a constant, so a is a constant, so z is what, because we're integrating with respect to dz. So we're going to differentiate what is inside with respect to dz. So if I differentiate a with respect to dz, it's going to be 0. And if I differentiate z with respect to dz, it's going to be 2z. Differentiate what's inside. So I'm going to have 2z times what I have 2z times 1 over my expression, which is z squared plus a squared, which is what I have here. Oh, wait. So I'm going to have 2 that over. Yes, so that is my integration for an expression z squared plus a squared with respect to dz. So I'm going to have the differentiation of what's inside times what I have over times the integration of what I have over my expression, which is what I have here. So I'm going to have, so I'm going to have this. So I'm going to have this 2z over z squared plus s squared, which is what I have here. But in this case, I have a half here. I have an expression here. I have a 1 here. So I'm going to have, wait, sorry. Oh yes, okay. So let me start explaining this again. Sorry about that. So explain how we got to that again. So I have an expression of, I have to integrate this expression here, but integrating this expression, I know that my derivative of an expression z squared plus s squared is equals to 2z. I integrate what's inside minus 1. This will be 1. Sorry. So I integrate what's inside times over my expression that I have here times 1 over half. So I'm going to have the 2 and these 2 are going to cancel. So I'm going to have this. So this is, I remember last time when I was teaching, I was talking about primitives of some functions. So I have a primitive z over square root of z squared a squared. And then my primitive for this function is this guy here. So if I integrate this guy, I'm going to get this guy here. So if I integrate z over z squared plus a squared square root dz, I'm going to get this guy here. So if I have this guy here, I'm going to have negative. Sorry, I'm going to have negative my constant, which is being gotten from this. So I'm going to have negative from the dv. So I'm going to have negative what I have my expression here, which is what I have. So I'm going to have the constant multiplied by the integration of ez, personally e to the dz, plus e is negative 1 or 1, and then plus what I have here with respect to dz, which is what I have here. So I'm going to have this plus this. So if I integrate e with respect to dz, e can either be 1 or negative 1. I'm going to have z. So if I integrate this, if I integrate dz with respect to z, I'm going to have e times dz, because the integration of dz is going to be z, so which is what I have here. Plus, if I integrate this, this is the primitive of this. So if I integrate this, I'm going to have z squared plus s squared plus a constant. You know that when you're always integrating, you have to have a constant. So I'm going to have this, which my final answer is going to be equals to my constant, which is not 6, it's a constant, a Greek constant. I'm going to have this, the constant over 2 pi epsilon 0 times ez minus z squared plus s squared plus a constant a. That will be my my potential. And then we're not going to find the potential on two parts for z less than 0 and z greater than 0, because we've replaced our difference by epsilon 0. So this potential is both for z greater than 0 and z less than 0. So the bringing in of this constant here was just to make our work easier, so that we don't have to find potential on both points or on both sides. So our E, which was our only difference in the answers of SHA, we had -1 and we have +1. We just replaced it by E for us to just be able to simplify our work and find our potential just on one point. That is why we replaced it with E. And then when we, let me explain it again. And then when we, so we're trying to calculate V, and then we know the expression that we have for V. So we know that E, the relation between E and V is E is equals to negative grad of V. And then coordinate Cartesian, we learned what our gradient of V is. So we learned that our gradient of V was the constant dV over dx in the direction EX, or in the direction E, if you want, or in the direction EX, plus this dV over, I think Cartesian is like the simplest, so we're going to have this over dy in the direction J, which is my EY, and then plus this dV over dz in the direction K or EZ. This is my dV. This is my grad V, coordinate Cartesian. So where there is my E, I'm going to replace with my E that I found, and the E that I found was this. The E that I found was this. And then it's in the direction K. So I do not have E in the direction I do not have E in the direction J. I only have it in the direction K. So I know that E is equals to negative grad of V. So if my grad of V is negative, if my E is equals to negative grad of V, I introduce a negative here because we do not have it here. So I mean here to be, so here to be 0, because we do not have it in the direction E, plus we also do not have it in the direction Y, but we have it in the direction K. So we're going to have negative grad V, which is what I have here and what I wrote here. So my E is going to be equal to negative grad V, which is what I have here. So my E is this, equals to negative dV over dz, which is what I have here. And then if I continue here, I'm going to have, so if I continue with that, I'm going to make dV the subject of the formula because I'm trying to calculate potential. So potential, I'm going to make dV the subject of the formula. For me to make dV the subject of the formula, I just multiply the dz the other side. So I'm going to have dz is equals to, dz times this is equals to negative dV. So I do not want a negative V, I want V. So I'm going to divide by the sign. So I'm going to have dV is equals to negative of everything that I have here times dz, which is what I have here. And then moving on, I have, I'm still trying to calculate V. So I have dV now. So I'm trying to calculate V. I integrate dV. So I integrate both sides of the V. So I integrate dV. I'm going to have V. If I integrate this side, I'm also going to see what I have with respect to Z. So I have, if I integrate this guy here, so I'm integrating this guy and this guy with respect to dz. So if I integrate this guy with respect to z, this is a constant. This is either 1 or -1. So I'm going to have this. I'm going to have E times dz. This is the same as E times dz if I multiply them. But then we're trying to find the integral. So if I find the integral of dz, it's z. So this is what I have here. So I'm going to have the negative this constant times e, the integral of e dz, which is what I have here. And then this is a primitive. This guy is the primitive of this guy. So this is a primitive of this. We're going to do more of primitives in analyze. So this will be a walkover when you do primitives, but this is a primitive of this. So if you have this as a primitive of this, you know that when you integrate this, is going to give you the primitive, which is what we have here, which is what we have here. So if I have, if I do my integration, I'm going to have Ez, sorry, I'm going to have my Ez plus my primitive of what I have here. My primitive of this is going to be z squared plus s squared, which is what I have here. So I'm going to have negative my constant over 2 pi epsilon 0 Ez plus z squared plus s squared plus constant. Don't forget integrate what you have plus a constant. So this is my constant a here. So this is my, because I was integrating both. So I have an integral of this and plus an integral of this. So I have the constant of this plus the constant of this, which has just been simplified to a as a constant a. So if I multiply this, I'm going to have negative the constant over 2 epsilon 0 times this. This is going to be negative and this is going to be positive. So which is what I have here, plus a as my v, as my potential. And then after that, they did the same thing, just combine it. So we have E, we have this indication saying our E is negative, is 1 when Z is greater than 0, and it's negative 1 when Z is lesser than 0. So they did the same with the Z that we have here. So the EZ, they said EZ is equals to negative, is equals to Z, CZ is greater than 0, and negative Z if Z is less than 0. So if you want here, you can put your modulus to indicate that you are finding at negative 1 and 1. And yeah, that will be your potential for both points on negative when Z is greater than 0 and when Z is less than 0. Are there any questions? Are there any questions, queries, additions, subtractions, anything?
During integration, so does it mean that the reason why you were not putting limits to that integral sign, it's because you have different limits of E and Z?
Yes, because we're trying to find the potential on different sides. So I didn't try to put the limits, but we know because we have the E. The E is a reminder that we're finding them at 2. On 2, it's just a simplified expression from 2 areas, because the E is representing the negative side, and the E is also representing the positive side when Z is greater than 0, and when Z is less than 0. So that's why we didn't indicate the limit. Are there any queries? So this is how you go about answering them. So as you go on, I think this is our last exercise. As you go on, you get used. I know it looks like it's long, but as you go on and as you keep on practicing, you get used, and they'll be on the tip of your hands. And as you learn more, because the integrations here, I know it's a bit challenging. The primitives, you don't know what the primitives are, but as you learn more in analyze, which I believe you do primitives in your faculties, or NS will teach you, and you do limits as well. So it will just be a walkover, because it's just a combination of analyze and physics. So you have to know your expressions, how to derive them. And then now when you're switching them and we're trying to find the limits. When you're trying to integrate, that's when now you have to bring in your analysis knowledge that you have. But they're not usually complicated. These are basic primitives that we have here. Yeah.
Just a reminder, you didn't send this document.
The primitives.
This same solution. You didn't send.
Okay. Oh, okay. I'll send it immediately after we're done. So I think I'll end from here. So next week we'll do one last subtopic. So last time we're talking about conductors, and then we'll see what to do this Thursday, and I think we'll end from there. And
so, Charles,
yeah.
is it possible to send us the next document as well so I can go through it before we actually start doing it?
Sure, I'll try. Okay, I'll send for you. We're having a lesson on Thursday.
Okay.
Okay, I'll send for you. I'll send for you, but I have to prepare. So I cannot just send anything. I have to get from what you guys are able to handle, because it's a lot of information, you know. You have to, maybe it's information for semester 2 and you're just going to do semester 1, so I don't want to load you. So I have to pick out the simple things and then make something that's simple and send, but I'll send it before we reach Thursday, before we start the lesson.
Okay.
Okay, have a blessed day, and we'll meet next time, inshallah.